Good morning. Myself Dr. Paula Shapui, Associate Professor, Department of Chemistry, SI Ministry of Science and Technology. Today, I'll be talking about very basic concepts of organic chemistry. I'll touch upon uh, on hybridization concept, then electronic properties, then dipole moment, acidity, basicity, pK rules, homolytic, heterolytic fissions, then different intermediate species, carbocation, carbanions, free radicals, carbines. Then I'll talk about weaker forces, van der Waals, hydrogen bonding. And finally, we'll be talking about electrophiles, nucleophiles, and how they affect the reactions, addition, elimination, substitution reaction. So, what is organic chemistry? So basically, organic chemistry, organic compounds, it will come from living organisms, or inorganic chemistry compounds comes from minerals. So for example, ammonium cyanide, it's an inorganic mineral, but if you heat it, you will be getting urea. That's an organic compound. So generally, we consider organic chemistry means it's a carbon chemistry. Carbon must. So what makes carbon so special? If you see in a periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So this is the second row of the periodic table, and if you see atoms left to the carbon, it gives up the electrons because they are less electronegative, and atoms right to the carbon, they are more electronegative. They will accept the electrons, and carbon share the electrons. So that's the specialty of carbon. Now, if we talk about structure of an atom, we know that atomic model where protons are positively charged in the nucleus, neutrons are neutral, whereas electrons surrounding the nucleus in different orbitals, they will be negative charged. So that in atom as a neutral, it should have equal number of protons and neutrons. So for example, atomic number of carbon is 6, so it has 6 protons and 6 electrons, and of course 6 neutrons. Now if we talk about distribution of electron in an atom, so there are several orbital S, P, D, F orbital, atomic orbital will be there, and surrounding the nucleus, first cell will be S orbital, suppose 1 is, second cell will be S and P, means 2s and 2p orbital, third cell will be 3s, 3p, 3d, fourth cell will be 4s, 4p, 4d, and 4f. So similarly, in the s orbitals, it has one atomic orbital, means a subatomic orbital. P orbital having 3, d orbital having 5, and f orbital having 7. And in s orbital, maximum electron capacity is 2, p orbital is 6, d orbital is 10, and f orbital is 7. And that's why if we consider first cell, maximum 2 electrons can be accommodated, in second cell 8 electrons, third cell 18 electrons, and fourth cell 32. So like this, electrons will be accommodated around the surrounding the nucleus. So definitely, which is close to the nucleus, that is your first cell. S orbital is very closest to the nucleus, and when you go for more and more higher away, they will having higher in energy. Basically, with increasing numbers, energy increases. So if we consider about the relative energy of the atomic orbitals, so lowest energy is 1 is followed by 2s, then 2p, 3s, 3p, 3d. So if we go for higher atomic number, their energy will be higher. And that's why if you see hydrogen having 1s orbital, helium 1s2, lithium 1s2, 2s1. So these are basically electronic configuration. So first electron has to fill up, which is close to the nucleus, followed by the other orbitals. So it has to follow above principle that electron has to go to the atomic orbital with the lowest energy, and more than 2 electrons should not be there in one atomic orbitals. And Hund's rule, it tells that electrons should be in opposite spin. So these things already we have studied in our 10 plus 2 chemistry, and I am just recapitulating these things. So atoms on the left side of the periodic table, they will lose electrons. For example, lithium or sodium, they are they are electron giver basically. They will lose the electrons and forms protons or cations. Sorry, protons means basically for hydrogen it will be, if it lose protons, electron, that can be called proton. But atoms on the right side of the periodic table, they gain electrons. So that's what that electronegative atoms, fluorine, chlorine, they will gain electrons and form anion. So fluorine, it takes electron, it will give fluoride. Chlorine, it takes electron, it gives chloride. But hydrogen having some specificity, it can accept electrons, form the hydride ion, it can lose electron, it form protons. So that's what the specificity of hydrogen atom. Now, if you know, we know, all of us know the table salt, sodium chloride. So sodium chloride is formed. It's an ionic bond formed by the attractive forces between the two opposite charges. So suppose sodium ions, it gives the electrons, and chloride ions, it gives the electrons and take the electrons. So that's why it forms the cations and anions. And if you know its structure, sodium chloride is a face-centered cubic where each sodium ion is surrounded by 6 chloride ions, or each chloride ion surrounded by 6 sodium ions. And in each faces there will be other atoms will be there, and that's why it's the FCC, face-centered cubic lattice. Now, how covalent bonds are formed? So basically, when you have unpaired electron in the outer shell orbital of each atom, they can share the electrons and they can form covalent bonds. So for example, hydrogen, two hydrogen atoms, they can have one, they can share one electron and form the bond, and that's called the covalent bond. Similarly, two fluorine atom having one electrons, additional one electrons, unpaired electrons, they can form bond. Or if we consider about that hydrochloride, hydrogen chloride, so hydrogen share one electron, chlorine share another electron and form the covalent bond, HCl bond. So how many bonds does an atom can form? So if you see that oxygen, it can form 2 bonds. Nitrogen, it can form 3 bonds. Carbon, it can form 4 bonds. So that depends upon how many unpaired electrons maximum it can have in its outer orbital. Accordingly, it can pair with other atoms and form either single or multiple bonds. Now, if we see the periodic table based on the polarity and electronegativity, you can see the hydrogen electronegativity is 2.1, whereas lithium is 1, sodium 0.9. Now, if you go for right side of the electronegative, periodic table, you can see oxygen 3.5, nitrogen 3, fluorine 4. So that means if we move from left side to the right side of the periodic table, electronegativity increases, and at the same time in a same series, suppose halogen group where fluorine, chlorine, bromine, iodine, astatine, you can see that in this series electronegativity decreases from top to bottom. So there are three types of bonds you can consider. One is non-polar covalent bond, when the electronegativity difference between two atoms are less than 0.4. When there is a polar covalent bond, that means electronegativity difference is more than 0.4 but less than 1. And when ionic bond is formed, when the electronegativity difference between the two atoms are more than 1.5 or 2, and that's why different bond can be formed. And definitely ionic bond is stronger because of charge assisted interactions, whereas non-covalent bond, they are neutral. Now, what is atomic orbitals? If we talk about atomic orbitals, so atomic orbitals, they will have defined shapes. In that orbitals, electrons can be accommodated. Maximum 2 electrons can be accommodated. Now, there are several atomic orbitals. For example, 1s, 2s, 2p, 3s, 3p, 3d, all this. So generally, s orbitals are round shape. 2s orbitals, so whether it is 1s, 2s, 3s, all s orbitals are round shaped orbitals. And another things I just want to share that what is lobe? Lobe basically where the electron density is the minimum. We can easily uh, get information from the p orbital. Suppose p orbital is actually dumbbell shaped, whether it is a 2p, 3p, 4p, doesn't matter. So it will have there will be two lobes. One is positive lobe, another is negative lobe, and there is a middle. There is electron density is the minimum, and that point is called node, or that plane is called nodal plane. So it shows that suppose you are having the guitar, and with that in that wire, if you just touched upon it, just stretched it and leave it, you'll see that it will move just like a waves. So if we see these waves are moving in the upward direction, we can tell it's a positive lobe, and when it's moved in the lower direction, that can be called negative lobe. And the two corner where the minimum displacement is there, that is called node point. Electron density will be the lowest. Now, if you see about the 3p orbital, you can see 2px orbital where orbitals are moving along the x-axis. When it is along the y-axis, it is called 2py, and when along the z-axis, it is called 2pz orbitals. Now, how hydrogen is formed? So, as we told that when unpaired electrons, they will combine together forming opposite spin. They will share the electrons. So you can see one is hydrogen having one unpaired electron, and this is also one unpaired electron. They will share the electron and form the sigma bond. So basically, two waves. So they can reinforce each other and they can cancel each other. If they reinforce each other, overall its magnitude will be higher. It will be constructive combination, and that's why the bond will form. When they will destruct each other, that means there will not be any bond formation. So it has to be in the same resonance or same plane, so that effective overlap between the two atoms or between the two orbitals, it will be there, and it will form the bond. So if we consider about the molecular orbital theory, there two 1s atomic orbitals, they will have combination with opposite spin. They will share the electrons and form the sigma bonding molecular orbital. And another case is the antibonding orbital, provided you have one more electrons where antibonding orbitals electrons are possible. In that case, we have to make sure that bond strength will be high when electrons are in the sigma bond in the bonding orbital than anti-bonding orbital, because anti means it will destruct it, bonding means it will construct it. Now if we see the p orbitals, how they can form, suppose two p orbitals, they will combine together and forming in same resonance, so it will be formed the pi bond molecular orbitals. So when we have carbon monoxide, the carbon having p orbital and oxygen having also p orbital with lower energy, so they when they will be forming, so they will be having the molecular orbitals in the bonding orbitals. So that's why it is stronger. Now, if we talk about how methane is formed, so methane basically carbon with the 4 hydrogen atom. And the geometry of methane is actually tetrahedron geometry, and the bond angle is 109.5 degree. Why? For that we need to understand the hybridization concept. So carbon outer electron configuration is 2:2p2. Okay, so when it is in the excited, state to form the covalent bond with other atoms, the 2s orbital electrons, it will promote it to the last p orbital, that is pz orbital. So now each carbon having 4 unpaired electrons, and these 4 unpaired electrons, they will combine with 4 hydrogen atoms. They will pair up and form 4 bonds. Now, when there are 4 sp3 hybridization is possible, they have the option tetrahedron geometry. So you can see here 1s orbital with 3p orbital, when they will be hybridized, you can see there will be sp3 hybridization is happening it. And in this case, geometry will be tetrahedron geometry because the bond angle between the carbon and hydrogen, so that's a 109.5 degree. And similarly, we can think about ethane, where two methyl group with the one paired electrons, they will share the electrons and form ethane molecule. It's a CH3CH3. And similarly, ethane also, each carbon will possess sp3 hybridization and bond angle will be 109.5 degree or 6 degrees. So that's actually tetrahedron geometry. So when you talk about ethane molecular orbital, so sp3 atomic orbital of methyl, and this is the sp3 atomic orbital, another methyl, they'll share the electrons and form the sigma bonding molecular orbitals. Then there is no extra electrons that will be placed in the anti-bonding orbital. Now if we consider about ethylene, how ethylene is formed, first of all, ethylene having two bonds, one sigma and one pi bond. Now, in case of ethylene, if you see each carbon bonded with the two hydrogen atom and one carbon atom. So that means even though each carbon having 4 unpaired electrons, but 3 p orbital electrons will be paired up because there are 3 atoms are lined up to pair. One, there are 2 hydrogen and another is carbon. So one extra electron in the pz orbital, it will be unhybridized, and that's why this is sp2 hybridization, and these pz orbitals, they will be forming the antiparallel or lateral overlap, which is perpendicular to the internuclear axis, and that's why ethylene is sp2 hybridization because pz orbital is unhybridized. And you can see where this sigma bond is formed. So carbon forms sigma bond with two hydrogens and one with carbon. And how pi bond is formed? This is two pz orbitals, they are overlapping in a lateral fashion and forming the pi bond. So you can see that how this, so when it's a sp2 hybridization, it has to be planar structure and bond angle will be close to 120 degree. Now if we consider about acetylene, you can see acetylene having 1 sigma and 2 pi bond. So there are, even though there are 4 unpaired electron is there, but there is no one to pair up. First of all, one is hydrogen, another is carbon. So only s and p orbitals, they will be forming the overlap with the, so s and p orbital of carbon, they will overlap with the 1s orbital of hydrogen and 2s orbital of carbon, and that's why it's sp hybridization. And sp hybridization means it's a linear geometry. There are py and pz orbitals, they are unhybridized, and they will be participate in 2 pi bond formation. This means py orbital of carbon and py orbital of another carbon, they'll form the pi bond. Again, pz orbital of another carbon and pz orbital of another carbon still form the pi bonds. And in this way, each carbon atom of acetylene molecule is sp hybridized and it's a linear geometry. Now, if we talk about methyl cation or methyl radical, so what is happening in case of methyl cation? So pz orbitals is the empty orbital. That's why it will be sp2 hybridization because there is no extra electron. Similarly, in case of methyl radical also one unpaired electron is there, nobody is there to share. So again, methyl carbocation is methyl radical also sp2 hybridization. But in case of methyl anion, you can see one additional electron is there in the 2s orbitals and there is no one to pair up, and that's why it will be sp3 hybridization. It's similar to ammonia molecule. So what is happening in ammonia case? There are one lone pair of electrons is there and three p orbitals, unpaired electrons. They'll combine with the three hydrogen atom, and that's why ammonia nitrogen is sp3 hybridized, where it will be also forming the tetragon shape as methane or methyl carbanion. So this is a sp3 hybridization. But when we have ammonium ion, you can see that the lone pair of electrons it is providing to proton, and you can see this ammonia and ammonium ions both are also sp3 hybridization. But in case of ammonia, there is a lone pair of electron that is part of your tetrahedron geometry, whereas in here it is a similar to methane molecules, and that hydrogen CH bond will be part of this tetrahedron geometry. Similarly, in case of water molecules, water having two lone pair of electron, that is your 2 is to 1 is 2 is to 2p2, whereas 2p orbital electrons they will form covalent bond or overlap with the two hydrogen atom. That's why water is also sp3 hybridizations. And if you see their bond angle is 104 degree there because there are two lone pair is there. More lone pair according to VSE pair theory, lone pair more lone pair it will just repulse that covalent bond, and that's why bond angle is slightly shorter, 104 degree. Now if we talk about hydrogen fluoride, hydrogen having 1s atomic orbital and fluorine having 2 is to 2p2 2p5, so 1 pz orbital electrons they can form overlap and forming the covalent bond. Similarly, whether it is a hydrogen fluoride, hydrogen bromide, and hydrogen iodide, all cases bond formation is possible. But problem is hydrogen iodide is the least stable because atomic overlap between hydrogen atom and iodine is least compared to hydrogen and fluorine. Because in hydrogen and fluorine, it's a 1s versus 2p orbital, whereas hydrogen and chlorine it's a 1s versus 3p orbital, whereas hydrogen and iodine 1s versus 5p orbitals. Because of the size mismatch, effective overlap will not be that much good, and that's why bond strength will be weaker compared to hydrogen fluoride. So if we consider about that, summarize the hybridization, any kind of alkanes, it is sp3 hybridization, tetrahedron bond angle, tetrahedron geometry and 109.5 degree bond angle, whereas ethylene having sp2 hybridization 120 degree bond angle, and acetylene it is having sp hybridization and linear geometry 180 degree bond angle. Now, if we talk about the percentage of S character, we can see acetylene having sp 50% character, whereas alkene having sp2 hybridization 33% S character, whereas in alkene having sp3 hybridization. And as the S orbital is close to your nucleus, more S character, more stronger bonding will be there. So that's why acetylene molecule that shorter bond strength bond because it is much stronger, and also it has 1 sigma 2 pi bonds are there. So remember, more S character, more stronger bond. Similarly, when you go for less S character, it will have less bond angle, or more S character, more bond angle. So it's their kind of more S character, greater the bond angle. That kind of relationship are observed. Now, if we consider about the pi bond, why pi bond is weaker than sigma bond? Because pi bonds are lateral overlap and there is no effective overlap because overlap will not be that much strong. And if you consider strength of double bond 174 kilocalorie and strength of sigma bond is 112. So we can calculate what is the strength of pi bond. That's a 62 kilocalorie. So experimentally also we can prove that pi bond is weaker because of lateral overlap. Now let's move to several electronic effects. So what is electronic effects? Electronic effect basically electron movement through sigma or pi bond. So there are several electronic effects are there. One is inductive effect, mesomeric effect, hyperconjugation effect, electromeric effect. And if we see the strength, mesomeric effect is the strongest, then hyperconjugation, then inductive effect. So let me talk about one by one. Suppose the resonance effect or mesomeric effect where you have conjugated double bond, single bond are there. So because of that, electron can move from one corner to the one end to the another end. As a result, there will be partial positive charge and negative charge will be formed and dipole will be created. So more electron movement will be there, that effect will be much stronger. Now, for a conditions for resonance is first of all it has to be conjugated system. Another has to be the functional group has to be there so that it should have either lone pair or negative charge or positive charge should be there. So that is also similar to your mesomeric effect where suppose you consider about carbon with the two bonds, then double bond CH, CH double bond CH, NO2. When you have the electron withdrawing group, NO2 group is there, electron movement from that A towards this left side to right side. As a result, this bond strength will be very high and it will be forming permanent dipole. Now, there are two types of mesomeric effect. First of all, it can have electron donating group, for example, oxygen, NH2, NHR, amine, and fluorine, chlorine, bromine, iodine. So they can be electron donating group series and electron withdrawing groups. It may be nitro, or it can be cyanide, it can be acid, it can be amide, it can be ester. So those compounds can be electron withdrawing group. So both either donor or acceptor groups is attached to an conjugated system. You will observe mesomeric effect and that is very much strong. Now, why mesomeric effect? It is very important because you can have uh, so we can have mesomeric effect in regular compound like acetic acid or ethanol. Suppose why acetic acid is more acidic than ethanol? Acetic acid, if you consider a compound is acidic when its conjugate base has to be strong or stabilized. In case of acetate, because of that carboxylate ions, so negative charge can move between A and C, whereas in case of ethanolate ion, there is no possibility of movement of electron. So that's why acetate ion is more stable and ethanol than the ethanolate. So more stable conjugate base, that means acetic acid is stronger acid. Similarly, if we consider about this phenol, cyclohexenol and cyclohexanol, because cyclohexanol, if you take corresponding conjugate base, means phenoxide ion, you can see multiple number of resonance hybrid structures, and that will stabilize it compared to cyclohexenol, hexenol in ion. So as a result, phenol is more acidic than the cyclohexenol. So similarly, there are several examples we can discuss about it. So one thing is that whenever you have resonance effect, and inductive effect. So inductive effect, I think I have not discussed about inductive effect. Basically, it is a single bond affair. So suppose the carbon with multiple number of carbon is there, and if you have chloride ions at the end, so chloride ions, because of its more electronegativity, it will try to attract the electrons towards itself. So electron movement will be from left to right side, but there will be also permanent dipole will be formed, but as it is a sigma bond, electron that atoms which will be directly involved with the electron transfer, that will be creating partial positive charge or partial negative charge. So now let's come to these resonance structures. So resonance basically related to aromatic compounds, because this is more applicable. Uh, it has a conjugated pi bond system and compared to aliphatic compounds, and that's why resonance is more synonym with the aromatic system. So here we'll be talking about benzene structures, resonance energy, how it is applicable and how it stabilizes it, and what are the effects will be there that we'll discuss. So if we consider benzene bond length, it's a 1.42 angstrom. But if you know the regular molecules where the double bond is there, that bond length is 1.33 angstrom, and single bond is 1.52 angstrom. So why it is so? Because it has resonance structures. So if you consider about its calculus structures, so basically all the bonds are equivalent. So whether these two are double bond and this is single bond doesn't matter. All bonds are equivalent and it will form benzenes, and that's why each bond are equivalent and bond strength is same, because this pi bond is formed by the overlap of p orbitals, which is perpendicular to the planar sp2 hybridized benzene ring. So that's why you will be seeing that there will be pi orbital electron cloud over benzene ring. So 6 pi electrons are able to flow continuously around the pi molecular orbital formed from the 6p atomic orbital on each of the 6 carbon atom. So this is represented, so this is actually two resonance hybrid structure, or it's called canonical structures. And pi electrons are referred to as being conjugated. Now, resonance basically it will be responsible for stability, right? So if I consider about ethanolate ion, it is difficult to form. But if I consider acetate ions, it has conjugation is there between the two oxygen atoms involving carboxylate, so that is easy to form. So you can see here that carboxylates, that charge is moving from lower to the higher region, so that shows that resonance is happening in it. So as there are two resonance hybrid structures, so that's why acetate is more stable compared to ethanolate. Now if we consider about these molecules with the positive charge, that means resonance is happening it, shifting of or double bond is happening it, and that's why this is stable. But if we consider about this one, here also shifting is there, so both are stable. But problem is, when you are talking about carbon with the negative charge, carbon is the less electronegative with the negative charge, and carbon with the positive charge, this is more feasible compared to this one. So let's talk about nitro group, how it affects resonance hybrids of benzene. So nitro group is electron withdrawing group, because nitrogen having the positive charge. So it will withdraw electron density from the benzene, so that there will be positive charge created in the ortho and para position. So basically carbon ortho and para positions, if you want to go for electrophilic substitution reactions, it will not take it because already it's a positive charge, electron deficient species. So electrophilic reaction is not possible in case of a NO2 group attached to benzene because it deactivates the benzene. But comparatively, meta position is comparatively more electron dense than ortho and para position. So possibility of electrophilic substitution in the meta position is better, and that is also under harsh condition. Very high temperature you need to perform the reaction. But if you consider about methoxy group attached to the benzene ring, it has a lone pair effect and it will push the electron density towards the ortho and para position, and you can see there are ortho and para position negative charge. With the negative charge it can easily have electrophilic substitution reaction in the ortho and para position. So that's the difference. Whether methoxy group, it will have ortho para orienting group and it will easily form electrophilic substitution reaction, but nitro group, it is actually destabilizes the benzene ring. Electrophilic substitution reaction will not be so easy. So now come back to the inductive effect. Basically, it depends upon electronegative atom attached to the compounds with the sigma bonds. So we can see that fluorine is more electronegative than hydrogen from the inductive effects. Now let's see how inductive effects play a role. Suppose fluorine is more electronegative than the carbon. We know fluorine is more electronegative than carbon, or oxygen is more electronegative than carbon. So because of that, fluorine, chlorine, oxygen, it will withdraw the electron density from carbon. As a result, you will be having partial negative charge on higher electronegative atom. But if we have carbon attached with hydrogen, methyl or tertiary butyl group, they are donating group because they are pushing the electron density. They don't have electronegative atom. So as a result, they are having positive I effect. Whereas electronegative atoms having negative I because they are electron withdrawing. Now if we consider about propyl chloride, propionyl chloride, so electron density is highest in case of chlorine. So chloride will have negative charge and adjacent carbon will have the partial positive charge. But other two carbons will not have much effect because most inductive effect is observed the adjacent carbon atom only. And size dependent, inductivity is size dependent. Now if we talk about inductive effect and carbocation stability, we can see that when carbon with more number of methyl group is there, that is more stable than carbon with no methyl group. So you can see here among tertiary carbocation, secondary, primary and methyl carbocation, tertiary carbocation is the most stable than secondary, then primary, then methyl carbocation. So that can be explained based on the inductive effect of methyl group, and also we can talk about hyperconjugation effect. So you can see here three methyl groups push the electron density towards the carbocation. As a result, it will have more electron density. It will be stabilized. So I think we have talked about these bonds. Non-polar covalent will be when the electron difference is less than zero point 0.4, and polar covalent bond will be less than 2, and ionic bond will be more than 2 to 4 range. So for example, in case of ammonia, nitrogen and hydrogen, so difference is 0.9, and that's why ammonia is a covalent bond. Whereas aluminum chloride, it's a 1.5, still it is a polar molecule, polar bond. But magnesium oxide, it's a 2.3, that means a ionic bond. Hydrogen fluoride is close to ionic bond, but still it is a polar bond. But when you consider our hydrogen molecule, it's a non-polar. So if you know the electronegativity difference between the two atoms, you can tell whether the bond is polar, ionic, and non-polar bond. So what is dipole moment? Dipole moment basically is a vector quantity. It tells about the separation of charges between the two atoms in a bond, and it has a magnitude and also it has a direction. In fact, dipole moment, if it is measured by the dipole moment, and it is, if the dipole moment is positive, we can tell it's a polar. If it is a zero, that's called the non-polar. So for example, hydrogen chloride, here chloride having the more electronegative atoms, so electron movement from hydrogen to chlorine. So as a result, chlorine having partial negative charge, hydrogen having partial positive charge, and that's why it's a polar molecules. And you see its dipole moment is 1.03. Generally, um, it's a positive value. That means it's a polar molecule. But in case of carbon dioxide, as carbon, even though oxygen atom, each carbon oxygen bond is polar, but when two opposite forces, they will repulse each other. With equal and opposite forces, they will cancel each other. So, and that is happening in case of carbon dioxide, because carbon dioxide, two opposite carbon oxygen bond means vectors, they will cancel each other. So as a result, carbon dioxide is non-polar even though individual carbon oxygen bond is polar. So generally dipole moment is theoretically can be described as a charge into radius. Charge of electron, that is q, and r is the distance between the two dipoles, and that can be measured in coulomb or dBi unit. Now let's see that carbon tetrachloride, similar to carbon dioxide, it's a non-polar, because carbon tetrachloride, even though each chlorine carbon chlorine bond is polar, but it is forming a tetrahedron geometry where the opposite dipoles, they will cancel each other. And same thing it is better in case of dichloromethane, where it is also sp3 hybridization, but in this case we can get the resultant dipole moment of two carbon chlorine bonds which are having the similar direction. Now if we consider about pyrrole, then furan, thiophene, so they have, because nitrogen, oxygen, sulfur is comparatively more electronegative than the carbon. So more electronegativity difference will be there, more dipole moment will be there. That's why pyrrole is polar than the thiophene. And if you consider about chloroform and carbon tetrachloride, chloroform having a resultant dipole moment is positive, whereas carbon tetrachloride resultant dipole moment is zero. And that's why carbon tetrachloride is non-polar and chloroform is polar. Even from the dipole moment uh, value, we can easily tell whether a molecule is a cis or trans. So cis isomers, suppose 2-butene, it has a dipole moment 0.33, whereas trans isomer is 0. So we can easily identify whether a molecule is a cis isomer or trans isomer based on their dipole moment value. So what are the uses? Dipole moment is highly useful to predict a molecule is a polar or non-polar, whether molecule is symmetrical or they should not have any kind of polarity. They will be non-polar compound, or you can easily distinguish between cis and trans isomer. Even it is possible to distinguish ortho, meta, and para, because para having completely opposite side, so it will have zero dipole moment, whereas meta and ortho having higher dipole moment, or they will be polar. So to summarize, molecular dipole depends upon on the geometry of the molecule. So when molecule does not possess any net dipole moments, So they can be called non-polar. When molecule possesses a net dipole moment, it can be called polar. Now, last part of the topic, let's discuss that acidity, basicity, and pK values. So, what is acidity? So, according to Arrhenius theory, acidity means it should ionize to give proton, and Bronsted-Lowry theory tells that it should be proton donor, and Lewis acid theory it tells that electron pair acceptor. And similarly, in case of bases also, it should give OH minus ion, it should be proton acceptor according to Bronsted-Lowry theory, and Lewis acids it should accept, it should donate electron donor. And that's what, that when a compound it ionizes as a suppose BH, it ionizes as a B and B minus and H plus, that means it's a acid. So what is ionization constant? Suppose acetic acid, it ionizes as the acetate ions and H plus. So Ka ionization constant will be concentration of acetate ion into proton divided by acetic acid. Now ionization, if it is more, that means it will be more stronger. That's why higher ionization constant, it will be stronger acid. But at the same time, pK actually it's a minus of log Ka. pK if it is a lower, that is considered as a stronger acid. So if we consider about, this is the case that hydrochloric acid is stronger acid than water, than ammonia, than methane, that depends upon the fluorine, that electronegativity increases, and as a result you can have uh, fluoride ions. Fluoride ions, it is better stable compared to oxide or nitrogen negative charge or carbon negative charge. So more electronegative anionic atom in the conjugate base, it will be better to accept the negative charge. Similarly, when we consider about the hydrogen iodide, hydrogen bromide, and hydrogen chloride and hydrogen fluoride, yeah, one thing we can tell based on that effective overlap. In case of hydrogen fluoride, effective overlap is stronger, and also the it is much easier for hydrogen iodide because it's to dissociate, because hydrogen iodide bond is weaker. And in case of carboxylic acid and alcohol, we can see that conjugate base stability in case of carboxyl is more than the um, alkoxide, so that's why it is having more acid. Now, if we consider about the carboxylic acid, phenol, alcohol, amines, and alkanes, it is observed that carboxylic acid pK is close to 5, whereas phenol is around close to 10, alcohol pK is close to 16, and like that. So, because carboxylic acids, it has conjugate base stability. Now, if we consider the basicity, basically it should donate the electron lone pair, right? And it should accept that proton. So similarly, when we talk about the uh, stability order, methyl minus, then NH2 minus, OH minus, and fluoride. Methyl minus is more because it's a more stable. It can easily give the lone pair, and because it's a less electronegative compared to fluoride. Fluoride is more electronegative, so it does not want to give its lone pair of electrons. Similarly, when we talk about fluoride, bromide, iodide, fluoride having the negative charge, it is available in a certain sphere, whereas iodide, because of its large atom, it is fully dislocalized. As a result, fluoride is stronger base. And similarly, when you consider about the phenoxide ion, it is having the negative charge availability compared to carboxylate, because carboxylate, it is having the resonance stabilized, so the charge will be neutralized. So let's talk about another topic, that is your fission. So a bond can be, if it is broken and shared by equal share, that can be called homolytic fission. So for example, XY, it will form a radical if it is shared by 1 electron. But heterolytic fission, that is happening when you have um, unequal distribution of electronegativity. In that case, one will be forming cation, another will be forming anion. So by the way, what is free radicals? Free radicals basically one unpaired electrons on that atom. So for example, chlorine, under heat or UV light, it will form the radical. And we can see the radicals, even though they are unstable intermediate species, but tertiary radical is more stable than the secondary, than primary and methyl radical, because these methyl groups, because of its inductive effect, it will push the electron density towards the carbon, and that's why it is a more stable. Even free radicals are stabilized by the delocalization. You can see that carbocations as similar to carbocations, because of the conjugation, carbocation is more stable. Similarly, radicals also, whenever conjugation is there, there is a possibility of more stable radical formation. So for example, benzyl radical is more stable than the cyclohexyl radical, or phenyl radical is more stable than propyl radical because of the conjugation. Even radicals adjacent to the carbon having the lone pair, also it can be stabilized. And what is heterolytic fission? Basically unequal distribution of electron during fission, and that will give cation and anion. So for example, carbocation is tertiary carbocation is more stable than secondary, than primary, and methyl carbocations, that already we have seen. Then why it is? Because the methyl groups will push the electron density towards the carbocations. But in case of carbanions, concept is quite different, because already tertiary butyl groups are there. It is pushing the electron density. After that, if you have the negative charge, then this overall will be highly unstabilized, destabilized. Whereas in case of methyl ion, that negative charge it will stabilize, because it does not have any extra electron density like tertiary carbanion. So that's why methyl carbanion is more stable than primary, secondary, tertiary carbanion. Now, what is carbene? So, carbene basically it's a two covalent bond, two unpaired electrons. So that can be triplet when two electrons are in the same spin, or singlet can be in opposite spin. So there are two types of carbene. One is singlet carbene, another is triplet carbene, and both are intermediate species. Even triplet carbene is much less stable than the singlet, because triplet carbene having two electrons in the same spin, so they will repel each other, whereas singlet carbenes, it is having the opposite spins, that's why it is more stable. And last part of the talk, I'll just try to complete. So van der Waals forces. So what is van der Waals forces? This is the combination of intermolecular forces having attractive and repulsive forces. So if you see that when two atoms will become closer to each other, provided the distance is zero point 0.4 to zero point 0.6 angstrom, and when two atoms are very close below zero point 0.4 angstrom, that means they will repulse each other. And when it is going beyond zero point 0.6 angstrom, then they will again attract each other. So both attractive and repulsive forces are responsible for these van der Waals forces. It's a distance dependent. Whereas hydrogen bond is quite different. Hydrogen bond basically electrostatic forces that binds hydrogen atom with the electronegative atoms. So basically it is very much important for a supramolecular chemistry where molecules will be assembled together via hydrogen bond or any other weaker forces. So basically when hydrogen bonds are very much directional, and bond angle will be close to 180 degree, and it should have higher electronegative atom, then that bond will be very strong. So for example, hydrogen fluoride is very strong hydrogen bond, or water molecule can form easily strong hydrogen bond because the electronegativity difference is quite high. So there are two types of hydrogen bond. One is intermolecular, another is intramolecular. Intermolecular means between the two molecules. Intramolecular means between the same molecules. So that's the thing. And last part is nucleophile. Nucleophile basically it's a similar concept of the base, so it will attract the electrophile and to form the bond. So for example, Lewis bases are nucleophile, OH minus, then chloride minus, or tertiary amine group. And that's why the electron, so basically nucleophile and electrophile, they are complementary to each other and they can form easily bonds. So you can see OH minus take the proton and it will form the water molecules. Similarly, when you have the molecule, so this is a nucleophilic substitution reaction where nucleophile attack on the carbon attached to a living group, you can get the new bond. So that is called the nucleophile electrophilic electrophile. That is a kind of complementary to each other. But electrophile basically they are electron deficient species with the positive charge. So for example, tertiary carbocation or trifluoroborane or aluminum chloride, they are Lewis acid, so they are electrophile. They need to combine with nucleophile to form the new bond. So three classes of nucleophile. It should have the lone pair, it should have the negative charge, and it should have smaller size. Then nucleophilicity can be strong. Even the pi bonds also can be effective nucleophile because of its donating capacity. So benzene is highly strong nucleophile, or alkene group is strong nucleophile compared to the electrophile. Even sometimes sigma bonds are also nucleophile. You can see that BH4 minus sodium borohydride, it gives that nucleophile to form a alcohol.